Today I might be going over my most important video ever. It's something that's not really taught in school, but it really makes your understanding better about linearity and Thevenin's theorem in general. If you're watching this, you probably already know what Thevenin's theorem is. I'm going to go over kind of a rough example of how I understand it to be true, and show also how source transformations work, and I'll give some examples of that. So if you were watching the previous video, when I found the output impedance of my signal generator, um, you remember that I set up a circuit like this, and I just kind of said we could treat it as a Thevenin voltage with a Thevenin resistance, which is the output resistance we're solving for. And as we changed our load resistance, we're able to plot points on this IV curve, and then we would find the slope and know that's the output resistance. So check out the last video if you want to see how these plots were made. There's a Desmos setup I have with all the equations and stuff, and we said that as resistance increases to infinity, you get closer and closer to this x-intercept here. And so what we did was we found the slope based on these points, but what if we were able to find the points on each of the intercepts? So when the voltage is maximum and the current is zero, and the current is maximum and the voltage is zero. So let's just call these points V star and I star on these ordered pairs here. And as before, we know that we're defining resistance as voltage across something over the current entering it. So here, when we're defining current like this, it's the opposite of that. So it's voltage across divided by the negative of the current leaving. And remember, slope is change of y over change of x. So when we're finding the resistance, we're really finding the opposite of 1 over the slope because we draw our IV curve this way. And yeah, that's just the basics, but it's nothing too crazy. You know, you can convince yourself that this is why. And so really what Thevenin's theorem comes down to is this isn't the real circuit inside. We're just saying we can approximate it like this. And it doesn't have to be this. We could also have a current source with some other impedance inside of there, and it would work the same way. Basically, what Thevenin's theorem is saying is if we can find something that satisfies the same relationship here, then we can treat it as the same circuit. So this could have 100 components or 1,000, and as long as it follows this linear relationship with the same exact intercepts and everything, we can just say it's the same circuit as this. So to give an example of that, let's find a current source and a resistance that satisfies this exact relationship here. So first of all, let's find the intercepts, because we know if we can find these intercepts, we have the slope already from 2 points. These are the easiest points to find if we have hypothetical resistances. Of course, we couldn't have an infinite resistance and a zero resistance and measure it. So let's see, if the resistance is infinite, then this guy is just an open circuit. And we know that the voltage across here, which we were trying to find, V star, is just the Thevenin voltage that we defined as this guy here. So now if the resistance is zero and we're trying to find the maximum current, then this is just a short circuit here. And the current is just the voltage over the output resistance. So it's just this voltage over this resistance. And so now the slope, based on how we defined it, is just the V star over I star, or V Thevenin over the short circuit current here. And yeah, that's why sometimes you'll see, to solve Thevenin circuits, I'll show this later, one method is to find the open circuit voltage and divide by the short circuit current to find the Thevenin resistance. And that's basically saying this here, which is pretty neat. So if we wanted to find a current source to satisfy some relationship like this, we just need to maintain the relationship of that IV curve, find the two easiest points, and it turns out that these are the values you need. So the I star that we found before um, just follows this relationship here. So it's just the V Thevenin times, V Thevenin over the R Thevenin, and then the R Thevenin stays the same. So let's verify that. If this resistance is a open circuit, the voltage that is seen across it is I star times R Thevenin, because the current only flows through here. And yeah, that's exactly what we expect. Now, if this is a short circuit, no current flows through here, and all the current I star flows through here. And if we connect dots, yeah, that's the same exact relationship. So that states that anytime we have a situation like this or this, these are interchangeable in circuits. So is because they're just following the same IV relationship curve for any linear elements connected to it. So let's take a circuit example here. I'll start out just with this half here. This is, if you didn't know anything about source transformations and you're given the circuit, you'd probably use nodal analysis, use KCL in each node, two equations, two unknowns, do some algebra. This is solvable, but it's kind of a pain. You have to, multiply and organize all your terms and stuff, substitute. Whereas if you were to recognize that this current source in parallel with this resistance is just connected to some outside network, just as before, we've proven that this satisfies the same IV relationship as a voltage source in series with the resistance. And what is the value of that voltage source? We've proven that it's just the current source times the resistance in parallel with it. And the resistance stays the same for the source transformation. So if we were actually just subbing this back in here, what we observed is we can write it like this now. Just notice we've swapped this out for this and combine some resistances and whatnot. And now we're left with just one node that's unknown. And we can totally solve this whole circuit with just one equation and one unknown. So it really simplifies your life to do source transformations. And next video, I'll do a detailed explanation on how to solve any Thevenin circuit. There's 3 ways, and yeah, stay tuned for that.